Okay, so in this lesson, we're going to look at equivalent Boolean expressions. So let's start with a Boolean variable called homework done, and we'll let that be true. There we go. And another one that says room is cleaned, and we'll let that start out also as true. So if homework is done and your room is cleaned, and then we'll system.out.println, you can go out with your friends. Okay, else system.out.println, you cannot go out with your friends. Semicolon. Okay, so if we go ahead and compile and run, so when our room is clean and our homework is done, right, true and true, we can go out with our friends because true and true is true. Now, if we were to take this expression, homework done and room cleaned, and we negate it, so we're going to put an exclamation point in front, right? That's now the opposite. Homework done and room cleaned, if that evaluates to true, the not operator makes that false, and so now it would print the second result, the else. So we're going to switch these then so that it still works. So you cannot go out with your friends, right? You can go out with your friends. So if we run that and test it out, right, our homework is done, our room is cleaned, you can go out with your friends. Now, looking at equivalent Boolean expressions, okay, we're going to look at something called De Morgan's law. So in De Morgan's, what happens is we can distribute this not operator over the parentheses as long as we change the and in the middle to an or. So that would mean not homework done or not room cleaned. Okay, so let's think about what that means in the context of this scenario. So if your homework is not done or your room is not cleaned, right, then you cannot go out with your friends. So let's go ahead and test that and see. Well, I think I have an extra. I do. I have an extra parentheses there. So we'll try that again. And we can see down here, you can go out with your friends, right? Because homework is done, room is cleaned. And these two expressions on line 9 and on line 14, these are equivalent expressions. And that rule is called De Morgan's. So now let's look at some more equivalent Boolean expressions, this time using integers. So we'll say int x is 1 and y is 2 and z is 3. So system.out.println and we'll just let this be a Boolean result so we can compare these expressions. So if we had not x less than 3 and at y greater than 2. Okay, so if we were to check this to see how it evaluates, x less than 3, right, x is 1, 1 is less than 3, so that's true. Okay, then y greater than 2, 2 is not greater than 2, so this is false. True and false is false, then we get the negation of that, which makes it true. Okay, so this would output true. Now let's see if we can write another equivalent expression. So if we apply De Morgan's, right, we can distribute that not operator to the x less than 3. We change the and to an or, and then our y greater than 2. Okay, so we distributed the not operator, right, over the parentheses, and we changed this and to be an or. Okay, so let's go ahead and run and see if those are equivalent. Okay, we got true both times. So these two expressions are equivalent. Okay, let's see if we can write a third expression that is equivalent to the first two. So if we have x less than 3 is not, right? It's the opposite. The opposite of x less than 3 would be x's that are greater than or equal to 3. Okay, then we could keep our or the same, and then not y greater than 2, right? That would be the y's that are less than or equal to 2. So let's go ahead and evaluate. And there we go, right? We have 3 equivalent expressions. All 3 returned true. So 3 Boolean expressions, all very different, but they are equivalent. So we talked about De Morgan's. There are some other laws of logic that apply for evaluating equivalent Boolean expressions. So for our notes, we'll have a Boolean P, which is true. Q will be true. And then we'll make another one called R, and we'll let that start out as true as well. So De Morgan's has 2 versions, so system.out.println, and if we have a not operator in front of P or Q, right, that is going to be equivalent to distributing that not operator, so not P and not Q. So again, we distributed, let me space that out a little so we can see it. So we distributed this P or Q became a not P and not Q. Then we will copy and paste to get the other form of De Morgan's. So we're going to change this to an and we'll change this to an or. Okay, so not P and Q, right? We distribute and that becomes not P or not Q. Okay, those are called De Morgan's law. Now we're going to look at one called the laws of absorption. And in the laws of absorption, okay, we're going to start with P and then P or Q. Okay, and we want to see, is that equivalent to what? So if P is true, right, true and then we have true or. The true or short circuits, and that evaluates to true. True and true is true, right? So that's the same value as the P we started with. If P was false, okay, then we have false and that's going to short circuit and return false. So again, it matches the value of the P. So the law of absorption right, says that we're going to absorb all this other stuff, and the answer is just what we started with, right? The P that's in the front. So space this out, make it a little more readable. Okay, that law of absorption also works if this is an or and this is an and. Okay, so both versions of that are going to evaluate to P. And then we're going to look at the distributive laws. And the distributive laws say P and, then this will be Q or R. Okay, so P and Q or R. And that is going to always be equivalent to distributing this P and. So this will be P and to the Q. So P and Q. Or, so we'll put parentheses around this P and Q, and then we'll have an or. And then we distribute the P and to the R. Right? So this will be P and R. Okay, so I think I went crazy with my parentheses here. We've got our first expression, P and Q or R. Okay, then that P and distributes to the Q. The P and distributes to the R. So I think I don't need this one. And then that gets evaluated. Okay, so those should be equivalent. Then let's go ahead and copy, paste, and the distributive law works with the or and reversed. So that would distribute to P or Q and P or R. Okay, and those would be equivalent statements as well. Okay, and I'm just gonna, before I run this, throw some parentheses to group these together, and we'll group these together. There we go. Space that out a little bit for readability. Okay, let's compile, see if we need to do some debugging. So I think I have, am I missing? I am. I'm missing a parentheses here. So I'm probably missing one there as well. And then we'll run it again. Oh, and there we go. So here's our two De Morgans, right? Those both evaluated to true. Here's our two laws of absorption, and then here's our two distributive laws. And remember, that'll work for any combination of P, Q, and R. So if they're all true, if Q, excuse me, is false, right? If the R is false, whatever combination you can think of, right? These laws, because they're laws for equivalent forms of the Boolean expression, they're going to always evaluate to true.